In this video, we talk about marker traits. In particular, we concentrate on the copy, clone, send, and sync traits and explain what they do. Let's start simple. If I have a struct, we have already told you that if I do a let b is a here, I get move semantics. That is, the value behind the variable a is moved into variable b, and I'm no longer allowed to use a afterwards. If I activate this here, I get a compiler error, borrow of moved value a. Right. So this works, and it moves the value. If I use the derive copy and clone, to which we will get in a second, then this changes. If the type point is copy, then an assignment like this here will automatically make a copy, and I can use a and b afterwards. The clone trait is a super trait of copy, so therefore I need both of them if I want copy. So whatever is copy must also be clone. This deserves some explanation. Copy is a pure marker trait. By marking such a structure copy, I imply that a pure byte copy of the data in here is a valid copy. Therefore, the compiler can just copy the data here. Clone, on the other hand, is a proper trait with methods. So let's look at that. The clone trait has two methods. One is clone, makes a copy of the object it's called on and returns that. Whereas clone from is used like this here. If you do a.clone_from at b, then this is equivalent to a is b.clone. Let's see this in action. So either I can do here a.clone and make a copy of a, or I can declare b here, say as another point with 0, and then I make it mutable, and then I can call b.clone from reference of a. If I compile this, I also got 2 times the same thing. So let's recall, copy is a marker trait, clone has proper methods, and you can actually implement it. What you need is a clone and a clone from method. Note that if you implement clone for a type, then clone from is automatically implemented. As you can see here, this is just a declaration, and here is a default implementation. The default implementation is *self is equal to source.clone, where self is mutable. Most scalar types are copy. Like for example here, an integer can be copied. Note that I have a generic test function here, where the trait bound on the generic type parameter is copy. So therefore, I will get no error if a type is copy, but for example here the type string is not copy. Therefore I get here, when I try to compile this, the trait bound string copy is not satisfied, the trait copy is not implemented for string. So integers, scalar types are copy, immutable references are copy, but many pointers are not copy, smart pointers, and string is not copy, because a byte-wise copy of the variable here is not a valid copy. Let's now talk about the send and sync traits. These two are often perceived complicated or difficult, but they are crucial for the concurrency story of Rust. So you need to know three things. 1. A type is send if it is safe to send it from one thread to another. Second, a type is sync if it is safe to use it concurrently from different threads. 3. A type is sync if and only if a reference to it is sent. These are useful to understand these marker traits and to know what to do with them, but you don't have to know this yourself, because send and sync are derived by the compiler automatically from the knowledge it has. Most elementary types are both send and sync, except some pointers, of course. And you get the following automatically. If a struct consists only of send and sync types, then it is automatically send and sync. And likewise for only send and for sync. We will now look at our smart pointers and see whether they are copy, clone, send or sync. To this end, I've written test generic functions where I have put trait bounds to the template parameter. So if I try to call test copy with a type which is not copy, I get an error. So let's see what happens. Here, for example, I have a box. As you can see, there are errors for copy and clone, but no errors for send and sync. So a box, even a mutable box, is not copy, not clone, but it is send and it is sync. So why is it copy, not copy? Well, copying byte-wise the pointer would break the promises of the box, because then there would be multiple pointers pointing to the same thing. Likewise, there is no clone implementation, so therefore these two traits are not fulfilled. However, it is send and sync, which is maybe a bit surprising in the beginning, but the usual borrowing rules ensure that nothing bad can happen even if these things are exchanged between threads. Let's now move on to the reference count type. It's not copy for the same reasons. You cannot have a copy, byte-wise copy of the pointer. That would break the guarantees. But you can clone it. If you clone the reference counting pointer, the reference count is increased. That is all well, and the borrowing rules are enforced, because you can only get immutable access if there's exactly one reference. But it's neither send nor sync, because the reference counting is not done with atomics. So therefore it would be inherently safe to work in different threads with the same thing. So therefore RCs are not send and not sync. The cousin ARC, atomic reference count, is for the same reasons not copy, but it is clone, but it is send and sync. So you can send arcs between threads and can access things in different threads. That's all fine. That's what they are built for, because the reference counting is done using atomics. Now, a mutex is naturally not copy and clone. You don't want to copy your mutex objects, but you can easily send and sync it because it is a synchronization primitive, so it's absolutely fine to use in different threads and even send it over there. What one often sees is the combination arc of a mutex of something, because that can be sent safely and reference counted safely, and then is protected by the mutex. If you get a mutex guard, then obviously you cannot copy or clone it. That's not intended. And you cannot send it. That is because most thread implementations, most mutex implementations don't allow to return a mutex when in a different thread than it was acquired. So therefore it's not safe to send a mutex guard. But it is safe to send a reference, therefore it is sync, because dropping a reference doesn't actually free the mutex guard and therefore doesn't unlock the mutex, so it does not do anything. So therefore, this is the case. The read-write block behaves exactly the same. You cannot copy or clone it, but you can send and sync it. After all, it's a synchronization primitive. And the read and write guards behave exactly like the mutex guard. Yeah? You cannot send it, but it is sync. Coming back to the ref cell by nature is not copy or clonable, because this would break the guarantees of the cell. You can send it, because the usual reference, the usual borrow checker can ensure safety between threads. But you cannot, it is not sync, because if you send a reference to a different thread, then the counting of the mutability of the borrows is not done in an atomic way, so therefore it would break or would create data races. Exactly the same for the cell, naturally not copy and not clone, but it is send, you can send it because the usual borrowing rules apply. It is not sync because the guarantees are not done with atomics. This concludes our guided tour through the send and sync and copy and clone traits for the various smart pointers we looked at. I know this was a tough one. It took me quite a while to prepare this, and I'm still not sure that I understood the last little detail of it. But I hope that this video gets you started. Follow the links in the accompanying webpage for the documentation. There are some excellent articles to understand the last little details of it. And this knowledge here will be useful when we talk about threads, concurrency, and maybe async coroutines. Thanks for listening. See you in the next one.